Finally, we're ready to build the Raptor 50. But let me say a little something just before we get started. These little tips that I'm going to give you as we build the Raptor 50, I don't mean to criticize the Raptor 50 at all. I love the Raptor 50. If I didn't like the Raptor 50, I wouldn't be using it for this DVD. My point is, no matter if you have a Raptor 50 or if you have a $2,000 top-of-the-line helicopter, these little steps are going to be necessary for both machines to get them perfect, to get them kissy-kissy. So, as we go along, I'm not cutting down the Raptor 50, I'm just trying to give you the best built helicopter that you can have. One other comment just before we get started. I'm not going to show you every blow-by-blow assembly of the helicopter. If it's pretty straightforward, I'm going to assume that you can go ahead and do it. I want to point out the parts that really need attention so the helicopter is built right. As we start the build, just a word about fitting ball links. This will be a very important and reoccurring theme throughout the DVD. The first thing you want to do is just snap the ball link on the ball and get a feel for how much drag there is. Then go ahead and pop it loose, and after you do a few ball links you'll be able to tell. Go ahead and insert the tool and wind it a few times, and again you'll get a feel for this as you go on. After you've used the tool, it's a good idea to take a Q-tip and clean any residual plastic. There you can see plastic on my finger. Clean the residual plastic from the link because that will affect the fit on the ball. So you go ahead and snap it on, and here I got lucky. I've almost got perfection on this link on the first try. So you can see the idea. Go ahead and use the tool, clean it with the Q-tip, and fit it over and over again until you get a perfect fit. When it comes to fitting the ball links on the Raptor, you really have two options. One option is to use the JR ball link tool and fit every link on the helicopter. The other option is to replace all of the links with Rocket City links. These are perfectly sized to the ball, and you don't have to use the JR link tool to enlarge the diameter of this link. As a matter of fact, this plastic is softer and the tool really doesn't work well at all on soft plastic. If there's any weakness to these links, it's that when the link is molded, there's a very fine edge around the link. Now, these links can be snapped on both ways, and which is very, very good. And so, but when you snap on the link, this fine edge may fold over, and you'll find that one time the link is perfectly smooth, and the next time the link has some drag in it. So what you want to do is take an X-Acto knife that has a brand new blade on it, and use the very tip of the blade, hold it at a 45-degree angle, and just rotate the blade around the ball link. When you do that, you'll end up with a very small sliver of plastic, which would normally, this is what would fold over and interfere with the fit of the ball link. So if you use the Rocket City links, do this on both sides and they'll fit perfectly forever. Step 1, fuel tank assembly. The Raptor 50 comes with a thin feed line in the fuel tank. That's good because it makes the feed line very flexible. When you go from upright to inverted, this will follow along in the clunk. It wouldn't hurt to keep a close eye on this so that it doesn't deteriorate. If it shows any signs of deterioration, go ahead and buy a high-quality piece of silicone fuel line. They have all kinds of stuff for airplanes as well as RC cars. And before I slip this fuel line into the tank, I want to take a little piece of 20 thousandths safety wire and put a little wrap of safety wire at both ends of the fuel line so the fuel line, as it ages, it doesn't bloat and slip off of the fittings. Here's the safety wire on the clunk end, here's the safety wire on the top end, and notice how I have the little rubber grommet in the middle of the fuel line here. Now we're all set to assemble the tank. With the fuel tank assembled, go ahead and hold the fuel tank up to the light so that you can see the clunk, and then roll the tank upside down and back to upright, and make sure that the stopper goes to the bottom of the tank in each situation. Step 2, clutch bell assembly. First of all, take the clutch, take a Bounty towel with alcohol, and just wipe out the clutch lining. Make sure that everything's good. And then before you screw the pinion into the clutch bell, you want to make sure that this ball bearing is a tight fit on this pinion shaft. This, I've had to give considerable pressure to pop this bearing off of this shaft. This fits much better than the Raptor 50 kit that I built about a year ago. So you want to make sure if the bearing just slips on this shaft, take a piece of 1,000th brass shim and put it between the ID of the bearing and the shaft as you push it down. So the ID of the bearing must not slip on this pinion. Okay, we're going to back off the shot, use the greaser to grease this bearing. This bearing is very critical because it's spinning at engine RPM. So we'll back off the shot, I'll show you how we use the greaser, and we'll be all set with the clutch bell. This little deal is called the greaser, and it's available at better helicopter hobby shops. What it is, it's a little phenolic insert. I have it filled with grease. I prefer the Bosch grease from Schluter. And so it's filled with grease, and the way that it works is you take the bearing and you lay the bearing in it, then you take the pointy white end, put it in the ID of the bearing, and then push down until grease comes out of the bearing. There you can see it's starting to come. And now the bearing is perfectly full of grease, and that way you'll get the most life out of this clutch bell bearing. I've cleaned the ID of the bearing from the greasing procedure. Now I'm going to go ahead and clean the pinion shaft where the bearing goes. Make sure that that's nice and dry. Then I'm going to take some red Loctite. This is just insurance. And I'm going to put some red Loctite on the pinion shaft. And we'll spread it around a little bit with a toothpick just for even spread. Again, the red Loctite is a permanent stuff. Then we'll go ahead, lay the bearing in place. And then I've got a deep socket that I can put over the bearing, and I can push the bearing down into place. You don't want to bang on this. You want to put pressure and press the bearing in place. There we go. Then we can simply screw this assembly into the bell housing. It does not have to be screwed tight. The load on the helicopter as the helicopter flies will automatically tighten up this fit. There we go. The bell housing's all done. Step 3, mainframe assembly. Here we have bearings that go in plastic frames. If you should ever run into a bearing that fits sloppy in plastic frames, just take a piece of striping tape and wrap the striping tape, generally one revolution of striping tape is fine. So wrap it with one piece of striping tape. That will expand the diameter a little bit, and then that will make sure that the OD of the bearing does not wiggle in the plastic side frames. Again, the Raptor fit has been excellent here. I don't have to do this to the Raptor. But again, if you would run into that scenario with any other type of different brand of a helicopter, that's what you want to do to make the bearing fit better. The Raptor comes with these little plastic inserts that so that a screw goes in one side and a screw goes in the other side. They sell metal aftermarket pieces for these. In my opinion, the plastic ones are just fine. Just don't be a gorilla when you tighten down on the threaded screws. As long as you use moderate pressure, these plastic pieces are just fine. As you fit the clutch bell into the side frames, make sure that the start shaft is not jammed down on these bearings. There should be a slight amount of vertical play in the start shaft. Before installing the main shaft bearings, again, go ahead and use the greaser to give these bearings a good shot of grease. When you put the C-clip on the bottom of the start shaft, make sure you include this little washer. The part number is BK0584, and they have the part number in the instruction manual, but they do not actually show the little washer. So after you slide the washer down to the bottom of the clutch bell, then you can go ahead and slide on the C-clip. Anytime you have a set screw, use either blue Loctite or a little bit of thick CA. If it's a metal-to-metal joint, it really doesn't make any difference if you use blue Loctite or thick CA. However, if there's any plastic involved, use thick CA, as the blue Loctite will have a tendency to eat plastic. Now here's the auto rotation unit. I've flushed this Sprague bearing with WD-40. If you don't, sometimes you'll fly a dozen, 2 dozen flights, and then the Sprague clutch will hang up on the main shaft, or actually on this steel collar. So I flushed it with WD-40 in advance. Hopefully I won't have to take it apart after a dozen or 2 dozen flights to go ahead and do that. Then the steel collar goes through. Then you can take one of the C-clips or the snap clips, and with this snap clip there is a kind of a flat edge and then kind of a rounded edge. I always make sure that the rounded edge goes toward the brass spacer on the auto unit. As I said in the theory section, you have a choice of the white gear, which will give a driven tail rotor, driving the tail rotor all the time, or you can use a red gear from a Raptor 30 to have a tail rotor that is non-driven, that doesn't turn, to get a little bit more extra inertia for auto rotations. If you use the red gear, the only other thing that you'll have to do is just get some 3mm by 12mm long bolts, and then you can slide those in and tighten the red unit down. Step 5, washout assembly. Here's a washout assembly that I've just put together, stock. Look how the arm is stiff. Again, this is not a criticism of the Raptor 50. Notice how this flips up, and it's just stiff. It's not totally smooth. Now take a look at this one, and it is totally free. And when I flip the little thing, look how nice and free moving it is. What's the difference between this one and this one? Tender loving care and attention to detail. Let me show you how I made this one work so nice. The first thing to check is the fit of the pin as it goes through the washout arm. The pin is a snug fit in the arm itself and pivots on the outer part of the washout arm. So again, the pin is a tough fit through here and should be a smooth fit through here. You can see that when we flip this, we've got some friction there. This just ought to flip-flop back and forth. So what we'll do is we'll take this out, and we'll take a number 47 drill bit, which is 78 thousandths, and we'll just run the 78 thousandths drill bit here with our hands at first to see if that will smooth things up. I'll go ahead and do this test fit. Here's the first one, and then we can take the shaft, put it through, and we're a little bit better here. I'm going to do it a little bit more. I'll come back and show you. Here we are. This was done simply by spinning the drill bit through here with my fingers, and you can see now that we have a perfectly free moving part. The next thing to do is to go ahead and check how the part fits on the arm. You can see that there's a little bit of a friction between the two, so what we'll do is we'll lay this flat on the table on a piece of 320 sandpaper and just take a half a thousandth or a thousandth off of this arm. Here's the arm. You can just take it, lay it on the sandpaper, put a little bit of pressure down, and after a few swipes, go ahead, get your arm, and check the fit, and just progressively do this until it's a perfectly smooth fit. When fitting any kind of arms, whether they be washout arms or A-arms, whatever, hold the piece up to the light and see how the light comes through the crack. That will enable you to see if it's a tight fit here or it's a tight fit here, and then you can grind a little bit here or a little bit there, whatever's required with your Mata tool to get a perfect fit of the washout arm or the A-arm. If you find that the pin fits perfectly smooth in one hole of the washout arm, but just drags very slightly in the other side of the washout arm, what you want to do is chuck the drill bit up in a Mata tool or a drill and make sure there's a smooth shank toward the bottom of the Mata tool. Okay, so I'm going to identify this one is perfectly smooth. This one has slight drag. So what I'm going to do is put the one that fits perfectly smooth on the smooth part, and then I'm going to run the Mata tool on low just for a couple of seconds, and just that little bit of movement on the drill bit will make the other side fit perfectly. After about 5 to 10 minutes of work, now this side is kissy-kissy, just like the other side. Now we're going to look at the washout hub and examine how it fits the main shaft. In the introduction, I told you that the plastic units can be a little sloppy on the main shaft, and there you can see some of that slop. So what we're going to do is we're going to take a piece of thousandths thick brass tubing. I'm going to make it about 4 to 5 millimeters wide, and I'm going to make a mark about 4 to 5 millimeters in on this piece of brass. So what we're going to do is just slide that underneath up to my mark so that it's inserted about 4 millimeters. The reason that I don't want to run it down all the way is that I want to keep the center free off of the main shaft for minimum drag. Now what I'm going to do is take 1 drop of thin CA and apply it at the junction between the brass tube and the plastic, and then we'll check the fit. Now I've applied 1 drop of thin CA to the junction between the plastic and the brass. You may find that this may want to stick just a little bit on the main shaft, but that's okay. It'll just break loose. That's why you don't want to use too much CA. Then, with the piece of brass sticking out, take a sharp razor blade and just shave off the excess. And now you can see we've got a beautiful 1/1000th shim in here. So what we do is we go back and fit this on the main shaft. Go ahead and wiggle it. It fits better. It fits better already. And so what I'll do is add, we've got one on this side. I'm going to put one on the bottom on that same side, and then we'll come back and check the fit. Notice how I'm using a pin to apply the thin drop of CA. Put that on. Give it a second to set up. Then slide it off. Take the razor blade. Whack off the excess. And now you've got a plastic piece with just a barely perceptible amount of shim. You get the idea. I may go ahead and put a piece on the other side and see what I get, but already this is 100% better than what we started with. After further examination and playing with another piece, I've decided to stop with the two pieces. Notice how there's just very slight drag. If you get it just right, you can see that it drops down. But this is just a perfect fit, and so I'm going to stop while I'm ahead. Here I've attached one of the washout arms to the washout hub. You can see how there's just a little bit of drag in the system, so all that I have to do is just crack that bolt back open just a touch, and now look at that. Now I've got a perfectly free yet slop-free linkage. Now I'm going to start to fit the links of the washout assembly to the balls. It actually is going to go on this inside rotating star, but because it's easier to fit, I'm just going to work with the outside non-rotating star. The balls are going to be basically identical. If I put this on, you can see that this is just absolutely, totally stiff. The whole washout unit won't even pull it down. It's just totally stiff. So again, what's the secret here? Tender, loving care. Now I've worked this ball link for a minute or two. I did not increase the diameter of the JR ball link tool. I just spun it a little bit. I also took the arm off of the washout hub so that there would be less weight. And here you can see that we have just a beautifully smooth working linkage. And when I lift up the arm, she just falls down. There's just a very slight amount of drag there. But again, you can see that this is just almost feather perfect. We're better off just a shade tight because as the helicopter flies, these ball links will wear in. So this is well nigh perfect. You want to do this to every link in the helicopter. Now when I went to put this link on the inner part of the star, I found out that, see how it's basically sloppy loose? So I take back what I said just a second ago. These ball links can indeed be different. Here you can see that it's nice, but it's not sloppy loose. So I'll just swap this ball with this ball, and from here we'll make sure that we fit each link with the particular ball that it's going to fit on. Once you start fitting ball links, or in this case a washout arm, to particular balls, it's important that you mark the ball link, or again the washout arm, along with its particular ball. So you can see how I've made a little red mark with fingernail polish here on the inner star of the swash plate. I've also got a mark on the washout arm, so I know that this link fits perfectly on this ball. Step 6, mainframe assembly part 2. I've got the little A-arms that go up to the non-rotating portion of the swash plate. And again, look how I've made a little mark on the swash plate, and I've also made a little mark on the A-arm so that these get matched up perfectly. Again, I have sized this link. See how it has just very slight drag. Another way to check the accuracy of the link is just to put your finger up against the link, and just with light finger pressure on the side of the link, you ought to be able to rotate the link or A-arm back and forth with relatively little pressure. Look how the A-arms fit perfectly to these pins. So it just goes to show you that what may not fit properly on one part may fit perfectly on another part, and you have to individually evaluate each part as you assemble the helicopter. Now here's the elevator control arm, and again the A-arm. This fits tight. This ought to just swivel, even though we don't have a pin in here. And the secret to getting this kissy-kissy is to go ahead and chuck up a very fine cutting wheel in the Mata tool. These are, I call them wafers, and they're just very thin cutting tools. And then just basically hold a nice 90-degree angle and just touch it to the part very gradually to bring down this distance so that the A-arm will fit smoothly over the boss. After about 7 to 10 minutes of careful work, I've got a perfect fitting A-arm on the elevator control arm. Please note that all of the ball links and A-arms and washout arms in the Raptor 50 are unidirectional, so the washout or the elevator control arm and the A-arms, they fit in the helicopter like this, so make sure that the open end is on this side and on this side. And again, I've finished fitting this A-arm. Notice how I've marked it with a red dot, and again, this is the one with the red dot. So again, everything matches up. In my opinion, one-sided ball links are the most worthless thing that's ever been produced. Kyosho started doing this with the Concept 30, and it's a terrible idea because you can't make half-turn changes in the ball links. Rocket City, fortunately, makes a symmetrical link, and it's a lovely replacement for other types of ball links. As part of this step, we're adding the swash plate. Notice how the red marked A-arm is matched up to the red on the swash plate, and the plain A-arm is set up to the plain part of the swash plate. And we're starting to get an initial indication of how super smooth and how beautiful the control system is going to be. Here I've got to fit a screw and a ball link to the end of this bell crank, and to facilitate the screw starting to thread, you may want to take your X-Acto knife and just carve out a little 45-degree angle, just very slight, and that'll really help the screw engage in the hole. Step 7, Mainframe Assembly, Part 3. When you put in the main shaft and you put on this nut, be very careful that you only tighten this nut just so that it contacts the collar. If you tighten the nut too tight, it can distort the steel bushing, which can mess up the operation of the Sprague clutch. As we start to make up push rods, we have two options. One is to hold the push rod with a needle nose pliers and go ahead and start the ball link. There are tools available, little ball link tools available, and this is basically a tube with a little slot in it, and it slides over the ball link, and it gives extra leverage to screw the ball link on the push rod. The other option that I like to do is I like to take a small vice grip, clamp it to the push rod, and then simply hold the ball link in place and flip the vice grip around, and the inertia of the vice grip automatically screws on the ball link. It works very nicely. If you make identical push rods, this is where the dial caliper really comes in handy. Make sure that you don't have any flash on either end of the ball links, and you can take one push rod and lay it in and get a measurement on it, then simply pull it out, adjust the other push rod just by trial and error. You can get it within a half turn, and so the other push rod is perfect as well. One way to check that you've got a perfect ball link fit on the ball is to attach a 75mm push rod to a ball link, and it should have slight drag on it. You can see that if I position it off to the side, it will kind of hold out, but if I straighten the link, it will drop down. So basically with this 75mm push rod, it ought to drop down, and you can see that there's slight drag, so it's not sloppy free, but it's absolutely perfect for a new helicopter. Now I've slipped the washout on the main shaft. I've made sure that the red washout arm is engaged with the red mark on the swash plate. But look what I've got here. When I come around to snap this other washout arm on the ball, it is way out of whack. It's telling me that this washout arm has to go in farther. If that's the case, I'm going to remove the other washout arm and snap this one on, and I'll show you what I get in just a minute. With the other washout arm snapped on, now you can see that this link comes in too far. In other words, it needs to be moved out. So what that will do is it will require me to put some small shims in between the washout hub and the washout arm on this side of the washout unit. To accomplish this task, we'll use two shim washers. This one is 6 thousandths thick, this one is 20 thousandths thick, and we'll use one or a combination of both to achieve the spacing for the washout arm so that that washout arm lines up perfectly with the ball on the swash plate. Here you can see the shim washers in place. It took approximately 32 thousandths worth of shim washers to make the washout arm line up with the ball. When this job is completed, the washout unit will be a perfectly smooth fit on the main shaft. If the washout arms are not shimmed, it basically locks the washout hub on the main shaft. You can see that when I move the washout arms, it wants to move the swash plate. The washout hub doesn't want to slide at all on the main shaft. Step 8, engine assembly. The first thing to do is to thread the fan onto the crankshaft. But as I was threading the fan onto the crankshaft, I felt a galling as the fan reached the fat part of the crankshaft. Now, I thought that was due to possibly a little ridge left in the woodruff key area when the woodruff key was machined. So I used some tape to protect the front bearing, and then I used my Mata tool with a grinding stone, and I just lightly faced off the woodruff key area. You have to use a grinding stone here as the crankshaft is hardened. A file won't touch the hardened metal. Here you can see some marks left on the inside of the fan hub after I screwed it onto the crankshaft. This isn't necessarily a bad thing. It indicates the fit to the fan hub to the crankshaft is nice and tight, which will give the most accurate runout when the fan is in place. Here you can see some of the aluminum shavings from the fan. Make sure you clean these out before putting the fan on for the final assembly. To tighten the nut on the fan hub, you'll need some sort of crankshaft lock assembly. They sell some real nice phenolic units that come into the back of the engine at better helicopter hobby shops. I am not a fan of piston lock tools that go in through the glow plug hole. That puts a lot of stress on the connecting rod and on the piston. What I normally do is kind of a low-tech way to go. I use a piece of 3/8 dowel rod. This is the equivalent, metric equivalent is about 9 millimeters. And I've shaved, you can see how I've shaved it a little bit thinner than 3/8 on both sides. And then on the front, I've rounded it off just a touch. This rounded portion goes toward the front, and it fits down the throat of the engine like this. When installing the fan hub, you do not need this black thrust washer. Due to the way that this is machined, it'll ride up against the ID of the front bearing in the engine. As you tighten up the fan, you want to get a rag, or I have a couple layers of Bounty towels here so that you don't gall your hand on the fan. This fan hub assembly is really a double locking system. You've got the threads in the fan hub, and then you have the nut. So after you screw the fan hub tight, just keep the dowel rod in the throat of the carburetor, put some Loctite on the shaft, and then tighten up the engine nut. You can see how the crankshaft has really scrunched the wooden stick, but because I've soaked it with thin CA, I really don't have any wooden splinters to worry about to contaminate the crankshaft area. The rest of the clutch installation is conventional. I did notice that when I went to put this steel shim on the bottom of the clutch, that it really didn't slide on very nicely. The ID was too tight. So I took a little cylindrical Dremel grinding stone and used that to increase the diameter of the ID. And then after I did that, the little shim slipped on beautifully. Then, when you bolt the clutch to the top of the fan hub, make sure that you use blue Loctite on both of these 3mm bolts. Step 9, mainframe assembly. The first thing that we do here is mount the engine to the motor mount. But when I laid the engine on the motor mount with the proper orientation, I saw a gap at the back of the engine where it touches the motor mount. I think you can see that in the shot. After looking a little closer, I noticed that the engine fit fine in the front of the mount, but when I went to slide it back, the engine backplate bolt was contacting the motor mount here. Now I have two options. I can either take a little bit of material away from the motor mount, or I can take a touch of material away from the mounting lug area. Not wanting to weaken the motor mount, I think I'll just remove a little area, a little material from the mounting lug area. With a little bit of material removed from the backplate mounting lug area, now the engine sits perfectly flat in the motor mount and there isn't any contact between the two. Before you install any bolts with Loctite, go ahead and dip a Bounty towel in alcohol and then squeeze the bolt between your thumb and finger and spin the bolt with a wrench, and that'll make the bolt nice and clean so there's good bonding between the Loctite and the part. The manual doesn't show any washers between the engine mounting bolts and the engine lugs, but I think it's a good idea to add them. Let me talk just for a minute about the efficiency of the cooling system. The Raptor 50 has this big open area, and air can escape out through this area. This is particularly important if you have a regular OS 50 or any other engine that has vertical fins on the cylinder head. What you need to do is take a 40 thousandths butyrate plate and bond it to the side frames, and then this will keep the air forced over the cylinder head. I've cut a little hole here for glow plug access. This will really optimize the efficiency of your cooling system. Here's the OS Hyper installed between the side frames. Note that the top part of this cylinder head is essentially doing the same job that my 40 thousandths butyrate plate did on a conventional vertically finned cylinder head. So adding a plate here is not nearly as important as it is on the conventional cylinder head. Before you slip the engine in place in between the side frames, take a Bounty towel soaked with rubbing alcohol and go ahead and clean the surface of the clutch shoes. You want to make sure that this surface is not contaminated so there's no slippage between the shoe and the clutch bell. Step 10, landing gear assembly. Now, there's a carbon fiber plate that goes at the bottom of the side frames, in between the bottom of the side frames and the landing gear, and that comes with pre-drilled holes for the landing gear mounting bolts. However, those holes are a little bit short, and you'll have to take a Mata tool and a carbide bit and just elongate those holes down or toward the back just slightly to get this carbon plate to fit properly. You also have to file a clearance notch in the carbon fiber landing gear plate. Do this with a Dremel tool with a carbide bit, and its purpose is so the plate clears the cylinder head of the Hyper 50. Now the skids come with little plastic end caps, and before you insert the end caps you might put on a little bit of slow CA or a little bit of silicone seal, and then go ahead and just slide those in and then wipe off any excess slow CA or silicone seal, and that makes the skids look pretty. When you attach the struts to the bottom of the main frames, make sure that at least the front set screws are loose here so that this front skid can be adjusted fore and aft so that it matches up nicely with the holes. I've tightened down the rear set screw so that I have 40 millimeters of skid sticking back from the aft strut. And then once the struts are fastened on and everything is sitting on a flat surface, then I can come up to this front set screw and tighten it down. The main rotor head goes together beautifully. You can see that the flybar seesaw, it's just feather feather smooth back and forth. And you're going to spend most of your time with the rotor head just fitting all of the ball links. Again, very important to fit the ball links. In terms of the flybar length, what you want to do is just measure from the flybar control arm out to the end of the flybar. Each side should be the same. You'll find it'll be about 159 millimeters. Once you get all the flybar assembly and the levers done, then it's time to go ahead and work with the main rotor blade axle. And to do that, you're going to need some CV joint grease. This grease is made for rubber boots, so again, it's not going to harm the rubber, and you can pick it up at any automotive store. Now the flybar comes with these long set screws that are meant to thread in the front of the paddle, and then they go in and bite into the flybar. I've never really used these. What I prefer to do is take an X-Acto knife and make a nice 45-degree angle in the hole of the flybar, and just take your X-Acto knife and get a nice bevel going in there. Once you've got the bevel, you can thread the flybar paddle onto the flybar, and then just put a drop or two of thin CA, and it'll wick right inside this bevel and securely hold the paddle to the flybar. To attach the flybar paddles to the flybar, first take a small wrench and find out how deep the hole is in the flybar paddles. Then go ahead and transfer this measurement to the flybar, and let's say it's 30 millimeters. Come back in, say, 27 or 28 millimeters. And then I'm going to put a piece of tape right here and then screw the flybar on just so that it comes up and touches the tape. With the flybar paddle screwed on and roughly in the right position, just eyeball one of the flybar paddles so it's perfectly level with the flybar control arm. And then put a drop of thin CA on that paddle. Now I've CA'd this flybar paddle to the flybar, and I'm using some small X-Acto clamps to get the paddles perfectly level with each other. I've set this one up. This is the master paddle. Then off camera, I fooled with the pitch of this paddle so that its clamp lays perfectly flat on the table. The other way to do this is to put the rotor head on the main shaft and then eyeball the flat surface of this clamp with the flat surface of this clamp. To install the rubber dampers or donuts into the main rotor hub, take a little bit of CV joint grease, go ahead and smear it on the damper or the donut. I'm using the axle so that I can kind of hold everything in place. And then go ahead and smoothly slip the donut into the main rotor hub. Now put a little bit of CV joint grease on the ID of each damper. Then take a little bit and smear a little bit on the main rotor blade axle itself. And then go ahead and slide the main rotor blade axle through the main rotor hub. Here are these beautiful aluminum spacers that keep the bearings in the blade grip away from the damper in the main rotor hub. Then I've greased both of these radial bearings with the greaser so they're all set to go. They can be pushed inside the blade grip. And then we want to make sure that we get the orientation of the thrust bearing correctly. The thrust bearing has two flat races with little grooves in it, and you want to make sure that the one with the play goes toward the main rotor hub. The easiest way to find the one that has the play is just to slip it on the axle and it will wiggle around. The one that is a tight fit just barely slips on the axle, and there's basically no play at all in that one. To grease the thrust bearings, I use a tapered object. This is just a plain old center punch. I slip the thrust bearing on the top of that, and then just take the tube of grease and rotate the thrust bearing around and get a nice coat of grease all through the bearings. Then I'll do the same thing with the flat races as well, and then I've got a thrust race unit that's all set to go into the blade grip. I've slipped a radial bearing in the blade grip. Now I'm going to rotate the blade grip around, and I've got the thrust bearing on a toothpick, making sure the large ID race of the thrust bearing is going into the blade grip first, and then I can just kind of slip this in, and there's the thrust bearing in place. Make sure you do not forget a stainless steel washer that goes between the thrust bearing and the outer race. Here's that washer. You can just go ahead and dump that in, and then you can take the outer race or the outer radial bearing and push that into place as well. Now you can take the blade grip, slide it down over the blade axle, and the thrust bearing is going to be out of position. It's not going to be perfectly round, or it's not going to be perfectly centered in the blade grip. So what you want to do is take a screwdriver or a toothpick and just basically run that around to center the thrust bearing, and then when that's done, the blade grip will slip the rest of the way onto the axle. Here I've got 2 Allen wrenches in each blade axle bolt. I don't put any Loctite on these bolts. I just simply rely on the torque to hold the bolts in place. With the blade grips bolted onto the axle, each blade grip should be perfectly smooth. You can see that this one has just a little bit of drag in it. That's because I greased both radial bearings. This will free up after I put a couple flights on the helicopter. But if you have obvious drag in the blade grip, that's an indication that one or both of the radial bearings is bad, and they can be checked individually and replaced as necessary. To check a radial bearing to see if it's bad, just slide it over top of a tapered surface. Take your hand and put pressure, downward pressure, as you rotate the bearing. If you feel any roughness at all, the bearing is bad and needs to be replaced. It's important that you mark each part of the rotor head and which side it goes on. So I've got the blade grip marked, and it goes to this part of the hub. Then I've got the mixer arm marked, the flybar control arm marked, and then you can take the push rods. For instance, this is the push rod that goes to this mixer arm, and so I've got it painted red over the little Thunder Tiger logo. This way all the links stay consistent and nothing gets changed around if you disassemble any part of the rotor head. Here's the bolt that holds the main rotor head to the main mast. Again, it must be shouldered and the threads must only be at the end. This is particularly important if you have a helicopter that's not a Thunder Tiger, that's not a Raptor 50. Thunder Tiger has really done it right here. In full-size helicopters, this is called the Jesus bolt, because if it breaks, you go see Jesus. Now I've got a hoop. It's marked with red. It's matched up to the flybar control arm, and it's going to go on this way. So what you do is you just take this and push this over the blade grip. It may seem like it won't go, but it'll expand just fine. And then you can bring it back, pull it up, and snap it on the flybar control arm. There are 3 places on the helicopter where you need ball links where you can make a half-turn adjustment. One is on the throttle push rod. The other 2 are on the push rods up to the rotor head, from the swash plate up to the mixer arm on top of the rotor head. We want this because when we make a blade tracking change, we want to be able to make a half-turn adjustment to make that a nice, fine, change to get the blades tracking perfectly. I've elected to use the Rocket City link on the bottom on my Raptor 50. You can put it up here on the mixer arm if you'd like. But anyway, the Thunder Tiger ball has to come off. You have to screw on a Rocket City ball. And then again, this is the red link. The red link goes up to the red mixer arm. The bottom of it snaps in, and now we're all set to make half-turn changes in blade tracking. With step 12 completed, all of our hard work fitting all of the ball links is really starting to pay off. Notice that we have silky smooth fore-aft cyclic movement, we have glass smooth right-left cyclic movement, and notice that there is absolutely no breakaway force, or there's absolutely no stickiness around neutral. Let me tell you a story about that. In 1974, Don Chapman and I were flying our Cavan Jet Rangers in Kidron, Ohio. I had flown my helicopter and came back to the pits, and he went out and flew his. Halfway through the tank, he came back through and said, "Ray, would you like to hover my helicopter?" And I was really honored because back in those days, you really had to trust somebody to let them fly your helicopter. So I said yes. So I took his helicopter out and hovered it for a few minutes and couldn't believe the difference in how his helicopter felt versus how my helicopter felt. When I came back to the pits, I just told Don that, "Wow, your helicopter sure feels different than mine." I didn't ask why, and he didn't tell me why. Well, in 1986 at the Toledo Convention, Don and I were sitting around the table, and we were talking about how the thing that really separates an average helicopter from a great helicopter is tender, loving care. And Don brought up the point. He said, "Ray, do you remember back in 1974 when you flew my Cavan Jet Ranger?" And I said, "Yes, I do, Don." And he said, "The difference that you felt in that helicopter was the ball links and the smoothness in the control system." As I've gone through this Raptor 50, I can't even begin to think of trying to fly this helicopter with all the stock links. The control system would be bound up so tight that the servo just can't put a small minute change into the control system. So if you fly this helicopter with the stock linkages, it's like flying with your servos C8 in place. Or would you drive a car where you can only move the steering wheel an inch in either direction? No, you can't. So I can't emphasize enough that you really have to spend the time to get the linkages perfectly smooth. Otherwise, you might as well sell your helicopter and go back to RC airplanes or RC cars. Step 13, tail rotor assembly. Before I bolt the tail rotor gearbox together, I want to talk a little bit about bearings and putting Loctite on the shaft so the ID of the bearing does not spin on the shaft. Most of the time this is done by experts when they're building a helicopter for contest work, and they will basically take every bearing and put a little bit of blue Loctite on the shaft, then they'll slide on the bearing and let the Loctite set up. That guarantees, again, that the inner race does not spin on the shaft. There's also something called green Loctite, number 290. And Loctite number 290 is a wicking type of Loctite, so that if you have an assembled piece, you can take a toothpick and just touch it to the shaft, and the Loctite will wick in and lock the inner race of the bearing to the shaft. Now, I don't recommend that you use the wicking Loctite or even really the blue Loctite if you're learning how to fly, because if you crash and have to repair something, it just makes disassembly that much harder. But because I greased these tail rotor bearings with the greaser, they are going to have some drag, and I want to make sure that the shaft doesn't spin on the ID of the bearings. So I'm going to smear on a little bit of blue Loctite here and on the other side, and then assemble the tail rotor gearbox. Again, I love the Raptor 50, but there are a few things in the machine that drive me crazy. One is the design of the tail rotor hub. The tail rotor shaft has a little dimple in each end, and the tail rotor hub is designed to be slipped on the shaft, and then set screws go through and go into the dimples. Then the nut goes on the end of the set screw that holds the whole tail rotor blade grip in place. Anyway, with these set screws in the dimples, it is impossible to remove the tail rotor hub if you want to do tail rotor balance. And again, tail rotor and main rotor balance is the subject of another DVD series. What I've done to the Raptor 50 is I have drilled a hole in the tail rotor hub. Now, I did this one just by eyeball. It's not really critical, because basically if you get it centered, you want to get it set up so that the set screw goes down into one of the dimples on the tail rotor shaft. This way, I can put in the set screws with red permanent Loctite. Then I can assemble the blade grips, put on the nuts to hold on the blade grips. Then I can remove the tail rotor as a complete unit simply by loosening the set screw and sliding off the whole tail rotor assembly. Here's the tail rotor pitch change unit, and like everything else in the helicopter, you have to go through and make it right. Here's the linkage that goes out to the tail rotor blade grip, and again, the stock one is not terrible, but it's not really right. Here's one that I've gone through and made perfect. Here's the tail rotor bell crank as it attaches to the tail rotor gearbox, and of course we have the tail rotor pitch change mechanism here. This tail rotor bell crank is an extremely critical part of the tail rotor system. In stock form, the tail rotor pitch change mechanism fits extremely tight in the hole, and it is imperative that you take your JR ball link tool and loosen up that hole so there's a nearly frictionless fit between the ball and the hole in the bell crank. As I was assembling the tail rotor bell crank in the pitch change linkage, I noticed at the extreme end of travel that I was picking up binding. After looking into this further, the pitch change linkage, when it comes and reaches extreme travel, it starts to roll over, and this boss starts to bump up against the gray bell crank. So you have to relieve the edges of this boss so they don't bump into the bell crank. Here's the tail rotor hub and the bearings for the tail rotor blade grips. When you screw this nut on the end of the set screw, make sure that the nut is not too tight so that it doesn't squeeze or put a preload on these bearings. I use a little 5/1000 brass shim, and I slip it between the outer bearing and the nut. And I just set this up so there's just light drag on both sides, and then I'm assured that I have the perfect adjustment for the nut and that the bearings are not binding up. A quick check of everything after the tail rotor pitch change linkage is assembled shows that everything is perfectly smooth back in the tail rotor. When you install the belt down through the tail boom, it really helps to have a long dowel rod, and then you can simply go ahead and put the dowel rod to the belt and go ahead and push it till it comes out the other end, and it makes it real simple. Step 15, mainframe assembly. Now you can hold the whole tail boom by the belt, and the belt will basically align parallel in the tail boom. If there's any doubt, take a flashlight and peer down into the tail boom to make sure the belt is parallel. Once you're sure that the belt is parallel, you can go ahead and rotate the belt 90 degrees to the left and then install the whole tail boom and the drive belt in the mainframe assembly. Here's a hot tip to set tail rotor belt tension. Buy an extra tail boom control guide and cut just about 2 millimeters off of the back of it. Then, when you put just moderate tension on the tail drive belt, you should have a 1 millimeter gap between the front of the support and the back of the side frames. Then what you want to do is you want to take a Dubro 2.5 millimeter by 15 millimeter socket head cap screw and thread it into the hole in the guide. Then what you can do, well, first of all then, you take a little sheet metal screw and you screw this tail boom support into the top of the tail boom. That holds it securely in place. Then what you do is you take your Allen wrench and you tighten this screw so that it comes up against the back of the side frames, and by varying this screw a quarter or a half a turn at a time, you can achieve perfect belt tension. To avoid any damage in the event of a tail rotor strike, you want to keep the tail rotor blades relatively loose in the blade grips. You don't want them floppy loose, but again, if they should strike something, you want them to fold back easily. Once the tail boom is in place, setting up the tail rotor control guides is an extremely critical task. It may take you 15 or 20 minutes to get it right. What you want to do is start with the push rod snapped on the tail rotor bell crank, and then get these aligned just by sliding them around on the tail boom. And then when you've got them aligned as best as you can, to check the alignment, come back here and unsnap the tail rotor push rod from the bell crank, and this movement of the tail rotor push rod should be silky smooth, and I think you can see that that's what we've got here. It just slides back and forth with basically no movement. Once these guides are perfectly aligned, invert the helicopter and put a drop of thin CA on each guide. Now before you CA this guide on the front, snap the tail rotor push rod back in place and push the tail rotor push rod all the way back until the linkage basically bottoms out on the hub back here, and then set a millimeter or a half a millimeter between the coupler and this front guide. Once the tail rotor push rod works perfectly smooth, you can slip in the front part of the tail rotor push rod through the two guides, and then notice how the stock push rod does not just smoothly go into the hole. It bumps into the coupler. So what you need to do is reform this Z-bend slightly so that this push rod will seamlessly and smoothly slide into this hole. Otherwise, if you don't do this and you force this Z-bend into the coupler, it puts a lot of pressure on this guide, and that will just single-handedly ruin your tail rotor control. Here's the kind of fit you're looking for. I'm using the standard Raptor glow plug clip. You can see how it clips onto the top of the plug. And in the case of the Hyper, it's a little hard to get to the top of the glow plug. So what I've done is I've bent the end of it up a little bit, and to make sure that it doesn't ground out and contact the cylinder head, I've just slipped a little piece of neoprene fuel line over the end. Here you can see the hole that I've made with a Mata tool in the side frame. Again, it allows the glow plug wire to pass through nicely. It doesn't contact any part of the side frame. Then I've put a little hot glue on top of the carbon fiber plate so that if the wire comes down and touches the carbon fiber doesn't cut through it. Then underneath, you can see how the wire comes around. I also have some more hot glue to hold the wire steady, and then it comes around into the glow plug adapter. The nut from the glow plug adapter may interfere with this carbon plate, so I've removed a little bit of the material here so there's no interference between the two. Also, you'll have to make a little flat spot on the top of the aluminum plate so that it doesn't interfere with this plastic rib. Here's the brass tube that we JB welded onto the carburetor with carburation without compromise. And here's the fuel line that slips on that brass tube. It runs back. Here's the shutoff that will control the airflow into the brass tube. And then here is a 59 thousandths Dubro stopper that's on the end of the fuel line. You can see how I just have a little nylon zip tie zipped to the top of the header tank here. And then from the header tank, we have the feed line. It goes through a filter. Here's the shutoff into the engine, and we're all set here. Just as a note, I do not recommend that you run a filter on the pressure line from the muffler to the tank, because during an auto rotation, you want the tank to pressurize and depressurize as quickly as possible, and the liquid in the filter hinders this process. So only use a filter on the feed line to the engine. Steps 16 and 17, servo installation. Now it tells you to use a piece of electrical tape to wrap the lead to the bottom of the collective servo, and you want to do that. But you also want to do that to the elevator servo and also to the middle servo here, which is the tail rotor servo, so that these leads come forward without interfering with these arms. Notice how I've taken a little zip tie and tied the collective servo lead onto the tail rotor servo lead. If you look at the other side, the collective servo just comes out straight forward, so we don't have anything to do with this. But again, the throttle servo, I've got it taped up so that its leads exit forward as well. When you physically install the servos in the frames, here's something to watch out for. If you use the stock screw with the stock mounting plate, the screw only goes in 1 3/4 turns, and that's not very much. So I recommend one of two options, your choice. The first option is to get a 2.5 millimeter flat washer, which is relatively thin, and then use it under the stock screw. This will let the stock screws go in 4 turns, which is much better than 1 3/4 turns. The other option, if you want to use the stock plate, is to use 2.5 millimeter by 15 socket head cap screws. The 15 millimeter length will go into the plastic, and it will give a much more positive engagement than using the stock screw through this plate. The collective pushrod and the throttle pushrod will both be adjusted in Volume 2 of my DVD series entitled Bench Setup. Here's a top view of the collective tray. Notice how we're using the inside stud and not the outside stud. I'm also using two 2 millimeter nuts to space the ball out farther on this stud. That prevents binding of the push rod on the collective servo arm. Step 18, receiver and gyro installation. Let's take a minute and talk about batteries, battery monitors, and voltage regulators. First, the batteries. Most intermediate radios come with a 1000 or 1100 milliamp NiCad pack. This is a 4-cell pack, so it's 4.8 volts. The bad thing about this pack is that if you lose a cell, the helicopter is going to crash because of insufficient voltage. So to avoid that, I prefer running a regulated 5-cell pack. The 5-cell pack puts out 6 volts, and when used with a regulator, the regulator drops it down to 5.1 volts. So if I'm flying with this pack and I lose a cell, now I still have 4.8 volts to get the helicopter down in one piece. When I land, I look at my battery voltage monitor, I see that it's in the red, and I say, oh, I've lost a cell in my 5-cell pack. All that I have to do is replace the pack and continue flying. This is Century Helicopter Products onboard battery indicator. The part number is CN2016, and quite simply, it's the best battery monitor I've ever used. It's about $20 and worth every penny. It has 2 little dip switches on the sides that can be set for different voltages, all the way from 4.8 volts up to 8.4 volts. In my application with a 5-cell pack, I've got it set to 6 volts. On the other side, we've got a set of LEDs, and we've got 6 green LEDs, a yellow LED, and then 3 red LEDs, which indicate low battery voltage. So normally, this little indicator is mounted on the side of the helicopter, and when you land during the course of a flight, just take a look at this indicator and see if you're in the green, yellow, or red. If you look at this indicator and any of the red indicators are lit up, you know that you've lost a cell in your battery pack and you need to replace the pack before you fly anymore. This is a simple regulator, and this is all that's needed to drop 6 volts down to 5.1 volts. This little regulator is a few years old. It's at 5.48 volts. Most of the regulators now are 5.1 volts, so we'll just assume that this is a 5.1 volt unit. It's all that's needed to drop the voltage down. However, if the switch harness in your radio system fails, the helicopter will still crash. There are more sophisticated types of these regulators available, and it's called the perfect switch harness or a safe switch harness. Let me show you a few examples of those regulators. The 3 types of regulators are the Radio South regulator, which is sold through Radio South, Jim Odino's regulator, which is sold through Miniature Aircraft, and then the Duralite batteries regulator, which is sold through the Duralite company. I have flown with and used all 3 of these regulators, and they've all been great. At the moment, the most cost-effective one is the Radio South regulator. It's about $37. The Miniature Aircraft regulator is about $50, and the Duralite regulator is about $47. But the beauty of these regulators is that they each have a switch included. And the purpose of the switch is to keep the battery power off. So if this switch fails, the power will continue to flow to the helicopter, and you'll only notice that this switch has failed when you land. You flip the switch to turn the helicopter off, but the helicopter won't turn off. So this is just the ideal way to go. You've got a regulator to drop 6 volts down to 4.8 volts, and you have a switch that when it fails to the on position, so you'll never lose a helicopter due to switch failure. When you've got a voltage regulator, you might ask yourself, what do the leads do? Well, let me go through that real quick just so there's no question. First of all, the box lead on the Duralite regulator and the Odino regulator, as well as the Radio South regulator, is just boxed and it goes into the battery. Now, the Radio South regulator is installed in the helicopter, so the Duralite regulator is exactly the same layout as the Radio South regulator. So, obviously, the box lead goes to the battery. So we'll go ahead and plug this in, and then we've got 2 other leads. And the question is, which one is 5.1 volts regulated and which one is 6 volts that goes to the battery monitor? Well, the easy way to do that is that if the switch is on, the one that's 5.1 volts won't even bring the battery monitor alive. So all that you have to do is simply grab a lead and plug this into it, and the one that's 6 volts will go ahead and light up the battery monitor. The other one, again, just for grins here, we can plug that in, and whether the switch, okay, there we've got the switch is on, see that's in the red, so that's 5.1 volts. If I turn the switch off, the display goes away. So that's an easy way to tell if the switch is on or off as well. Now, the same thing applies to the Odino or Miniature Aircraft regulator. Again, this one goes into the battery. And it's a little bit tougher to tell which one the Odino regulator might be because both of these leads come out from the body. In the Duralite regulator, it's pretty simple. This is 6 volts because it comes out of the switch. So again, we're plugged in. We'll go ahead and make sure the polarity is correct. There we go. That's the unregulated lead. And then let's plug in here. Cycle the switch on and off, and here you can see it just jumps with just a little bit of light, but nothing really stays on red. So again, this would be the 5.1 volt regulated and the 6 volt unregulated that goes to the battery monitor. The secret to receiver installation is to make a plate out of 1/8 inch plywood. This gives more room to mount the receiver in the battery pack. It is 70 millimeters wide, and again you can use your freeze frame to kind of review the dimensions. The holes to mount it to the plate are 32 millimeters apart, and they are 30 millimeters from the end of the plate. Then we've got 2 holes that the Velcro strap can slip through, and those holes start 60 millimeters from the end of the plate and end at 85 millimeters from the end of the plate. There are 5 millimeters on either side of the holes. Then I've got some holes to mount the antenna. The first hole is 115 millimeters from the bottom of the plate. The next one is 130 millimeters, and the last one is 145 millimeters. I've simply soaked this plate with thin CA and sanded it down. It can also be painted black if you want a nice look. To mount the plate to the servo tray, just slide it so that the back end butts in with the front of the servo tray. Use the 2 holes to drill down through the plastic plate, and then use 2 3 millimeter button head bolts and slip those down through to bolt the plate to the servo tray. And that's all there is to it. To hold the battery pack and receiver in place, use a 3/4 inch wide piece of Velcro. 20 millimeters is the metric equivalent. Go ahead and stitch the fuzzy piece and the hook piece together in a square and then an X pattern. Then you can buy these little squares from the sewing store. I've stuck on a fuzzy square which will engage in the hook piece of the Velcro. So what you can do is slide the hook end through this way. You can slide the fuzzy end through this way. And then the hook will engage with the fuzzy, and that will hold the Velcro strap perfectly in place. With the plate and strap in place, you can lay down a piece of 1/2 inch foam rubber, the battery pack, another piece of foam rubber, the receiver, and we've got a voltage regulator to go into here yet. You can take the one strap, push down a little bit, take the other strap over, and now you've got perfect vibration isolation for your battery pack and receiver. For the receiver antenna, I love the Revolution base-loaded whip antennas. I've been using these exclusively for the past number of years. They work great. It's part number RVO1010. They cost about $10.50. Let me screw this one in place, and I'll show you what it looks like in just a minute. Here's the Revolution antenna in place. A stock Raptor servo screw works perfect to screw it to the plate. Then use a heat gun to blend it to the shape of the canopy, and then put a little piece of fuel line on the tip that will prevent it from rubbing back and forth on the inside of the canopy. When you mount the gyro, make sure that you have access to the limit pot and also the reversing switch. You can see how I've mounted this gyro 45 degrees out of whack, and that doesn't make any difference in terms of the gyro sensing what the helicopter is doing. As long as it's on a flat surface, that's great. After you've installed the gyro, you'll need to route the wires down along the right side or the left side of the side frames. I've chosen the right side with the JR500T gyro. Now, the wires fit into the tangs, and the tangs really work nicely. The secret to getting the tangs to work is to take a wide blade screwdriver, stick it in the tang, twist the screwdriver to open up the tang, and then before the plastic has a chance to relax, just slip the wire in the tang. Then the plastic will relax back together, and it's just a really neat way to get the wires in place. You'll probably need some servo extensions to get the leads up to the receiver, and notice how I have an extension here, and I've used a little piece of carpet thread to tie the 2 connections together so that there's no way that the extension can come out of this lead. Step 19, Body and Canopy Assembly. The secret to putting decals on a canopy is to make sure there are no pointy ends. You can see how I've really rounded this at the front of this decal. It's rounded on the bottom and rounded here at the back. As long as everything is rounded nicely, these decals will never lift off of the body. I'm using a scrap piece for an example, but if you want to round off a corner, you really don't want to take the scissors and try to cut around it. The easiest way to do it is to cut it straight and then take one 45, take another 45, and take a 45 of that and a 45 of that. And when you take a lot of different 45s, you'll end up with a nice rounded edge. Carefully lay out the pieces before you attach them. In the case of this side decal, this cutout has to be about 1/8 of an inch bigger than what's shown on the decal. Again, you can measure from top to bottom and get a distance, measure from aft to forward and get a distance, and cut this circle accordingly. In order to keep this top piece from lifting, it has to be substantially shortened. Notice how I've rounded it off nicely, and we're all set to put the decals in place. Here's the finished canopy. With the rounded edges, these decals will never lift during normal use. Notice how I've added a 1/4 inch piece of striping tape to the canopy. It really adds a nice accent to the windshield. For the vertical fin, you can never keep a rounded corner if you keep the stock length at the bottom and the top. So what I'll do is essentially cut part of the top off and cut a lot of the bottom off so that this will smoothly blend in to this bottom point. After I do that, you can kind of see what it'll look like, and here there's no danger of the decal coming off because we've got a rounded edge here, a rounded edge up here, and a rounded edge here at the corner. Here's how I've trimmed the vertical fin decal for the left side of the vertical fin. Let's go ahead and put it on. All that you need is a bowl of water, and put 4 drops of dishwashing detergent into the water and mix it up with your finger. It does not have to be soapy. Go ahead and wash the vertical fin in soapy water just to remove any finger or oil prints so that the vertical fin itself is perfectly clean. Then what you can do is just dip in the water and go ahead and get the vertical fin completely wet. Go ahead and peel the backing off of the decal. And then you can immerse the decal in the water as well, again, and just get it nice and wet. Go ahead and lay the decal in place, and the soap will let you slide around the decal a little bit. And I'm just going to position it here. And that looks good. Once you get the decal in place, squeegee the water from the center of the decal and basically work down and out. You don't want to trap any bubbles in here, so we'll just work down. And then the same thing with the top, work out from the center. And I use my fingernail along this ridge to make sure there's no water trapped in the reinforcement in the vertical fin. Then what you can do is take a Bounty towel and again work any excess water out from under the decal. And there's the finished product. Now we can go ahead and let it dry. After the decal is dry, take your fingernail and rub along the perimeter of the decal, and that will securely bond the edges of the decal to the piece that you're working on. The same thing applies with the horizontal fin. With the stock decal, there's no way I can get a rounded corner, so on this side I've shortened it and blended it in, and now I've got nice round corners on all of the decal so that these edges won't lift. Now there are other decals that have to be cut out from here, and that's why I've made these little inlet cuts. If those other decals weren't there, then I would just take this and just run this smoothly straight across. A lot of helicopters today don't even come with main rotor blades, but look what we get with the Raptor 50. 2 sets of blades. That's a great deal. Now, if you've been flying helicopters on a simulator, you can start with the carbon fiber blades if you'd like, but if you have no flight experience at all and you're starting from square one, you want to go ahead and build these wooden rotor blades. Now, building and balancing main rotor blades and also tail rotors is the subject for another DVD series, but I do want to say one thing about these wooden blades. When you attach the black root reinforcements to the blade, make sure that you take a knife and cut away the plastic covering. The black blade reinforcements must be glued directly to the wood. The final step in building the Raptor 50 is to take this pitch arm and flip the blade grip 180 degrees to get the pitch arm to come off the leading edge of the rotor blade. But when we do that, we have to get this linkage over on this side. To do that, I have to unscrew it here and screw it in over on this side. When I do that, it's going to interfere with the flybar control arm. So I have to loosen the flybar control arm and rotate it 180 degrees on this side. I have to do that for both flybar control arms. Now let's drop down and see what we have to do with the washout unit. Because I flipped the control arms up on the rotor head, the hoops are going to have to be flipped and they're going to have to come down on the opposite side. Because of that, the washout arm is going to have to be flipped as well. So in other words, instead of this bolt coming in from the left side of the main shaft as you see it, this bolt is going to have to come in to the right side of the main shaft. To do that, we'll remove the rotor head, take the washout hub off, rotate it 180 degrees, and drop it back on. Now, when we do that, this washout arm is going to have to hold the same orientation as it's flipped over to this other side. The washout hub is made to be snapped on one way, so that means the washout hub will be rather difficult to snap on, and that's just the way it is. Now, the washout arm is relieved on this side, and to get a full range of motion, we'll have to take a Mata tool and trim some of this plastic away. Another thing we'll have to watch for is that when we flip these arms 180 degrees, we'll have to make sure that the washout links line up with the balls on the swash plate again. Basically what that will entail is taking the washers and moving them from one arm over to the other arm. So just so that you're aware of that and watch for that as you swap this washout assembly around. The first thing that I'll do is disconnect the links up on the rotor head. Now, in order to flip the blade grip and get the pitch arm over to the other side, I'm going to have to remove this ball in order to do that. Now I'll remove both mixer arms in preparation to mount them on the other side of the flybar seesaw. With both mixer arms removed, go ahead and flip the flybar control arm over to the other side. To do that, loosen the set screw, and then you'll have to remove each ball so that when you flip the flybar control arm over, they don't interfere with each other. With the flybar control arm flipped, notice how I've ground a little bit of plastic away here so that the bottom of the flybar control arm doesn't interfere with the hoop. Well, this is now on the top side, so I'll have to grind away on the other side to maintain that clearance. When I flip the flybar control arm over to the other side, the set screw now goes down on the bottom. But if I pull the flybar control arm away, I see that I only have a flat on one side of the flybar. This means I have to rotate the flybar 180 degrees. Notice how this arm automatically comes to the right side, so I don't have to fool with that. However, I will have to flip the paddles 180 degrees so that they're rotating in the right direction. An additional bonus from getting this pitch arm over to the leading edge is that when I flip the flybar control arms, now it also puts the flybar control arm on the leading edge of the flybar paddle. The hoop now, instead of snapping on this side, has to snap on that side. So I'll have to remove the hoop, flip it 180 degrees, and slide it back on over the blade grip. In addition to flipping the hoop 180 degrees, I actually have to move it over to the other blade grip, in this case to keep the red hoop aligned with the red ball. These long push rods will also have to be flip-flopped on the swash plate, but because we used Rocket City ball links here, I really don't have to take the ball off. I can just unsnap this link and put it on the other side, and vice versa. Now we can take the red mixer arm, keep it oriented to the red flybar control arm, and now we can go ahead and bolt it into position like this. With the blade grip now flipped to the leading edge of the blade, I can screw in this ball and then attach the short linkage up to the mixer arm. In the stock configuration, with the mixer arm bolted over here, this short little piece is angled down slightly. Because we flipped the mixer arm, now this little piece is angled up slightly. That's no big deal from a geometry standpoint of view, but it does increase the distance between the mixer arm and the pitch arm. To take care of that, we want to take a stock Raptor link and we want to cut it off right where it says T on the T Tiger. So that's removing basically 3 to 4 millimeters of material. Then you can go ahead and take this link and screw it on, which I've already done, and this will ensure that the pitch range of the blade grip is very close to what we want. The distance from hole center to hole center will be about 32.5 millimeters. Now that everything's been flipped around on the top of the rotor head, and again here you can see that the pitch arm now comes off the leading edge, now we can go ahead, remove the rotor head from the main shaft, and we'll start to work on the washout and the washout arms. With the washout links unsnapped, now we can take this whole assembly, flip it 180 degrees, and drop it back down on the main shaft. And now all we have to do is go through our little alignment procedure to make sure that these links line up with the swash plate balls. Here you can see how I've trimmed out a little bit of material from the washout link to retain its full range of motion. This time it took two 20,000ths shim washers to get the washout hub perfectly smooth on the main shaft. The other thing to watch out for is when you reinstall the rotor head, make sure that the washout hub slides smoothly on the pins extending down from the main rotor hub. With the blade grip flipped 180 degrees, now the bolt comes in from the bottom with the nut up on top. Ideally, we want the nut down below. And let's go to the board and I'll show you how we can take care of that. Here's how to get a square peg in a round hole. Basically, you have points, 6 points, and you want to take these points and transfer them to the round hole. Once those points are transferred, you want to take a small Dremel carbide bit, and you essentially want to take a little material away here, here, at all of these 6 points as I'm showing you. When you've done that, the corners of the nut will fit into these areas that you've ground out, and then the nut will fit perfectly in the round hole. And there we have it. Now a perfect rotor head where the pitch arm comes off the leading edge of the blade. Also the flybar control arm comes off the leading edge of the flybar paddle. And the only difference now is that the collective arm will move down for positive pitch in the rotor blade and move up for less pitch in the rotor blade. Again, this makes no difference to the collective servo because the collective servo doesn't care which way it drives the swash plate. With everything really right in the rotor head, look what we have. The whole collective mechanism falls part way, and it's just perfectly balanced and silky smooth. Finally, we're finished with the build. What we've got here is a perfectly built Raptor 50. Now what I've actually been trying to do throughout this whole DVD series is really teach you how to think. So you take a part, you look at the part, and you visualize how it ought to work. Then you do what you have to do to make that part fit and work perfectly. After you understand that, you'll be able to generalize those principles from a Raptor 50 to any other helicopter that you have. Now, with this helicopter built perfectly, you're in a position to view volumes 1, 2, and 3 of my authoritative DVD series. Volume 1 talks about transmitter setup and transmitter theory. This helicopter is in a perfect condition to seamlessly blend into Volume 2, where we do the helicopter bench setup. From there, I take the helicopter out to the flying field, and within 3 tanks of fuel, get it flying better than the ability of 95% of the pilots out there. Thanks for watching, and I hope to see you in another edition of Ray's Authoritative DVD series. One more thing. Ever since I finished Volume 1, 2, and 3 of the DVD series, I've been looking for a pilot that's really proficient, that's really able to pull out the potential of my Raptor 50. That pilot is Bert Megbanwa from La Crescenta. What you're about to see is the first flight that he's flown on my Raptor 50. He just picks it up and does amazing things with it, things that I could never do. This is a tribute to Bert's flying ability, the Raptor helicopter design itself, and also a setup that's well nigh perfect. What you're seeing is the exact same setup that you'll end up with in Volume 3 with 2 exceptions. The first one is I'm using Magnum 15% fuel instead of Cool Power 15% fuel. And also, I'm using carburation without compromise. I'm using a 046, a 46,000th hole in the stopper. So sit back and enjoy Bert's magic. What do you think, Bert?
Great job on the setup, Ray.